Engaging. In the International Baccalaureate's ideal vision, the Collaborative Sciences Project is a seamless merging of minds, biologists, physicists, and computer scientists pooling their expertise to tackle complex, real-world issues. To make sure this happens, the IB mandates that every diploma and career-related program student complete a 10-hour interdisciplinary science project. But on the ground, school coordinators are left figuring out how to actually schedule it. You have to align cohorts across biology, physics, design tech, and computer science without breaking the master timetable. This project is entirely non-assessed, focusing on a 100-word reflection on team collaboration instead of a graded scientific product. This creates a tightrope walk for administrators. Overinvest your resources, and you eat into core syllabus preparation time. Underinvest, and those 10 hours devolve into a meaningless compliance exercise. This is the official IB checklist, showing exactly what the Collaborative Sciences Project must include to be validated. Some of these expectations are highly achievable within normal teaching structures, focusing on the process rather than a finished product, and allowing students to explore a global issue are straightforward pedagogical targets. But the logistical friction lies in these two specific rows. You have a hard 10-hour minimum, and students are strictly required to mix with peers from different science subjects. Because these core constraints are rigid, you cannot negotiate the requirements. The only variable your school actually controls is how you choose to schedule the time. To get through the CSP successfully, educators have to stop looking for a flawless educational model. You simply need to choose your preferred flavor of logistical friction. The first strategy is the intensive sprint. The IB suggests variations of this, like 2-day data hackathons or in-school art and science exhibitions. The required input is blunt. All science students and their faculty mentors are pulled completely off the master timetable for 2 consecutive days. The primary benefit is certainty. The 10 hours are completed rapidly, and student engagement remains hyper-focused on the task. The trade-off is a scheduling nightmare for non-science teachers, who lose their students. It demands intense, immediate allocation of lab space. The intensive sprint delivers highly effective educational results, but executing it requires spending massive upfront political capital with the rest of your school's faculty. The second strategy is the slow burn, which spreads the project out over several weeks or months. Here, the input relies on students self-managing their interdisciplinary meetings during free time. Schools often anchor this approach to long-term research on sustainable development goals. The core benefit is that it completely preserves the daily master timetable. Non-science classes proceed without interruption. The hidden danger is that this project competes with assessed coursework. Because the CSP isn't graded, student motivation drops, placing a heavy burden on mentors to maintain momentum. This model successfully protects the daily school schedule, but it transfers the friction directly onto your science teacher's daily bandwidth. The final strategy is the double dip. This unique approach integrates the project with existing service learning or experiential field trips. You merge science objectives with CAS projects, like having students use apps to catalog local biodiversity, or tasking them with testing water quality during a trip that's already on the calendar. The outcome is peak efficiency. You hit 2 separate IB requirements, CAS and the CSP, at the exact same time, saving programmatic hours. The trade-off is it requires heavy front-end coordination with your CAS coordinator, restricting student freedom to a pre-existing theme. While it looks incredibly efficient on paper, the double dip is only viable for schools that already have highly collaborative administrative structures in place. Choosing the right blueprint means identifying your biggest operational weakness. If timetable disruption is unacceptable, set up the double dip. If students struggle with self-management, use the intensive sprint. For micro schools, mix year 1 and 2 students biannually, running logistics every 2 years. There is no frictionless implementation of this project. Success simply comes down to choosing the constraint your specific staff is most equipped to handle. Once you lock in a model, you have to ensure your students and staff do not overcomplicate the end product. The ultimate deliverable is a 100-word reflection on team collaboration, steering clear of any expectations for a Nobel-worthy scientific discovery. The logistical hurdles, the compromises, and the messy communication required just to finish the project together, that is the actual curriculum.